Alright, now let's move on to the third and final part of this topic, projectiles. This entire time in kinematics, we've been dealing with one-dimensional motion. When an object moved upwards, it went straight up. When it fell, it went straight down. Everything happened along a single line, one dimension. Projectiles are different. For the first time in this course, you're being introduced to two-dimensional motion, where two separate directions are happening at exactly the same time. Let's understand this with an example. An object is projected at an angle of 30 degrees above the horizontal at a speed of 80 meters per second. What happens is that this object follows a curved path, a shape called a parabola. The kinds of questions you'll be asked here are similar to what we've already covered in motion upwards. But now, because we've genuinely got two dimensions, there's one new question added on top. Let's list them out. Find 1. Maximum height. 2. Time to reach maximum height. 3. Total flight time. 4. The duration for which the object is 50 meters above the ground. 5. And new to this topic, the range. The range is the horizontal distance the object travels, from where it launches to where it lands. On our diagram, that's this distance here along the ground. Before you can answer any of these, there's one essential first step for every single projectile question. Split the initial velocity into its vertical and horizontal components. Our object launches at 80 meters per second at 30 degrees above the horizontal. Using trigonometry, horizontal component equals 80 cosine 30 degrees. Vertical component equals 80 sine 30 degrees. Working these out, 80 sine 30 degrees equals 40 meters per second. That's our vertical component. 80 cosine 30 degrees equals 40 square root of 3 meters per second. That's our horizontal component. I'm deliberately leaving 40 square root of 3 as a surd for now, rather than converting it to a decimal. This isn't our final answer yet, and keeping the exact value avoids any rounding errors creeping into our later calculations. Only round to a decimal at the very end, once you reach your true final answer. Here's the important part. Once you've split your velocity into these two components, you can forget about the original 80 meters per second at 30 degrees. That number has done its job. From this point forward, think of this as two completely separate individual motions happening at once. One object moving vertically upward at 40 meters per second, exactly like the motion upwards section we just covered. One object moving horizontally at 40 square root of 3 meters per second, a new type of motion we haven't dealt with yet. The only thing connecting these two motions is time. Time is a scalar. It isn't tied to any direction. So it's the one quantity that's genuinely shared between the vertical motion and the horizontal motion happening simultaneously. Let's work through our first 4 questions, and you'll notice they're solved exactly the way we solved them in motion upwards, just using our new vertical component of 40 instead of the original 80. For maximum height, we use v squared equals u squared plus 2as, applied vertically upward. At maximum height, final velocity is 0. Remember, you're not using 80 here, you use 40, because we already split the original velocity into its vertical component. V squared equals u squared plus 2as. 0 equals 40 squared plus 2 times minus 10h, which gives us 0 equals 1,600 minus 20h. So h is 80 meters. Just like before, let's use v equals u plus at, applied vertically upward. 0 equals 40 minus 10t, and t equals 4 seconds. In this particular example, the motion is symmetric. The object starts on the ground and lands back on the same ground level. So we can use either method. Let's do both, just to keep our eye in. Method 1 using symmetry. 4 times 2 equals 8 seconds. Method 2, the better method. S equals ut plus 1/2 at squared, applied vertically upward. The object starts on the ground and ends on the ground, so the overall vertical displacement is 0. 0 equals 40t plus 1/2 times minus 10t squared. Simplify further and factorize it. We get t equals 0, or t equals 8 seconds. We select t equals 8 seconds, since that's the sensible answer for total flight time. For question 4, let's use s equals ut plus 1/2 at squared, applied vertically upward, with s being 50. So 50 equals 40t minus 5t squared. Divide everything by 5. 10 equals 8t minus t squared. This gives us a quadratic equation. T squared minus 8t plus 10 equals 0. Solving this gives us two values for t. T equals 4 plus the square root of 6, or t equals 4 minus the square root of 6. The duration above 50 meters is the difference between these two times. Delta t equals 4 plus the square root of 6 minus 4, minus the square root of 6 equals 2 square root of 6. Converting to a decimal. Remember, never leave your final answer as a surd. This gives approximately 4.90 seconds. Now the new question about maximum range. Looking at our diagram, the range is simply the final horizontal position measured along the ground from the starting position. Here's the key idea for this part. In the horizontal direction, there is no acceleration at all. Gravity only ever acts vertically downward. It never has any effect on horizontal motion. Think back to how the vertical component behaved. Starting at 40, decreasing through, let's say, 30, then 20, 10, down to 0 at the peak, then increasing again as the object falls, 10, 20, 30, back to 40 just before landing. It's constantly changing. The horizontal component does none of that. It stays at exactly 40 square root of 3 the entire time, at launch, at the peak, and at landing. Because there's no acceleration acting on it, it simply never changes. Since there's no ordinal acceleration, only one of our 4 Suvat equations is actually usable here, which is s equals ut plus 1/2 at squared. And because a equals 0, the entire second term vanishes completely, and we're left with simply s equals ut. Here, s is the range we're looking for, and I'll be using r to represent it. And u is 40 square root of 3, and t is the total flight time we already found, which was 8 seconds. So, r equals 40 square root of 3 times 8 equals 320 square root of 3. Converting to a decimal, r is approximately 554.3 meters. The example we've just worked through was a straightforward case. The object started on the ground and landed on that same level ground. Let's now look at some different scenarios, where the object doesn't land at the same height it launched from. Understanding these will give you a complete grasp of projectile motion. Case 1. If the object ends at a lower point. Here, the object is launched from a height at some angle theta and lands on the ground below, lower than where it started. So the overall vertical displacement is downward. Vertical. Initial velocity is u sine theta, upward. Acceleration is g, downward. Displacement is h, downward. Horizontal. Initial velocity is u cosine theta. Acceleration is 0. Displacement is r. Case 2. If the object ends at a higher point. Here it's the reverse. The object launches from ground level and lands somewhere higher, on a raised platform. The overall vertical displacement is upward. Vertical. Initial velocity is u sine theta, upward. Acceleration is g, downward, exactly as always. Displacement is h, but this time upward. Horizontal. Initial velocity is u cosine theta. Acceleration is 0. Displacement is r. Case 3. If projected horizontally. This one's special because the object is launched perfectly horizontally. There's no angle involved at all. Vertical. Initial velocity is 0. There's no vertical component at launch, since the object moves purely horizontally to begin with. Acceleration is g, downward. Displacement is h, downward. Horizontal. Initial velocity is simply u, the full launch speed since none of it was directed vertically. Acceleration is 0. Displacement is r. A few things stay true, no matter which of these scenarios you're dealing with. First, acceleration is always vertically downward, equal to g. That never changes, in any projectile scenario, ever. Second, none of these three cases are symmetric. Since the object doesn't land at the same height it launched from, you cannot use the shortcut method, doubling your time to maximum height, to find total flight time. That shortcut only ever works when the launch height and landing height are identical. In every one of these new cases, you must use the full method, s equals ut plus 1/2 at squared. There's one more thing you need to watch for in these scenarios. When you solve s equals ut plus 1/2 at squared using the quadratic formula, you'll typically get two values for t. In many of these cases, one of those values comes out negative and the other comes out positive. A negative time value should always be rejected. Time cannot be negative. This tends to show up specifically in situations where the object ends at a lower point than where it started. So keep a careful eye out whenever you're solving a lands below launch height scenario. And that's projectiles. Whenever you come across a projectile question, the method is always the same. Split the initial velocity into its vertical and horizontal components. Then treat each one as its own individual motion. The vertical component behaves exactly like the motion upwards and motion downwards work we've already covered. The horizontal component moves at a constant velocity, with no acceleration at all. And the one thing tying both of these motions together, the only thing they genuinely share, is time. And that's the end of kinematics. Everything on the sheet you're looking at right now. Grab it for free, along with a full worksheet and worked solutions. Links in the description. If this helped things click a little better, a like or a subscribe genuinely helps this channel grow. But either way, I'm glad you stuck around. Next up, momentum. And that would be the beginning of dynamics. See you there.